Okay, in this video, we are talking about radiation and temperature. So, all bodies emit radiation. And if you've ever seen or used an infrared camera, you'll have seen an image pictorially of the amount of radiation that different objects are emitting. And this can be pretty counterintuitive because it's not just hot things that emit radiation. Cold things emit radiation as well. It's just that cold things emit different kinds of waves to what hot things emit. And basically, it all comes down to the temperature of stuff. How intense that radiation is that it emits depends on how hot an object is, and the types of wavelengths of radiation that an object emits also depends on the temperature of that object. Let's have a look at an entirely overcomplicated graph. Okay, it looks bad, but I promise it's not too bad if we look at things one by one. This is a graph which shows the intensity of radiation which is released from objects depending on the wavelength of radiation that you are looking at. And each of these different lines represents objects of different temperatures. This one is a colder object and this one is a hotter object. So it's not too bad if we look at the different features one by one. The first feature, you can see that my hot object emits a higher intensity of all different types of wavelengths compared to my cold object. Or in other words, the graph of my hot object makes it higher up the y-axis than my cold object. The second thing you might notice is if you look at the wavelength, which is the highest intensity for these two graphs. For the hot object, you will see that that wavelength is smaller than for the cold object. The final thing is the sharpness of these graphs. The hot object has a much steeper incline towards that highest intensity and steeper decline. It is sharper. And the cold object is a much more gentle slope up and gentle slope down. It is a broader, less sharp pattern. Okay, so all objects emit radiation, and the type of radiation that they emit depends very much on the temperature of the object. So now we can ask ourselves the question, how do objects change their temperatures? Let's think of a little scenario inspired by my current situation. Let's imagine, like me, you had a hot cup of coffee, but you left it for too long because you were distracted, and now it's gone cold. What has been happening to that cup of coffee? Okay, so we know it's an object and it is emitting radiation, but it is also absorbing radiation. And because my coffee was hot, it is emitting a high power of radiation. And the power of radiation that it's absorbing is smaller than the power of radiation that it is emitting. So basically, it's losing more energy per second than the energy per second that it's gaining. And so overall, it loses heat to its surroundings and it gets cold. Okay, let's take the opposite scenario. Let's say it is a beautiful, sunny, hot day, which it is, and I'm stuck inside doing this. Anyway, let's imagine that you have got yourself a Coke to enjoy on the hot, sunny day, and again, you leave it, you forget about it, you're distracted, you come back, and the Coke's warm and flat. Now, my Coke, even though it is a cold object, remember, because it is an object, is still emitting radiation. And it emits a certain power of radiation. At the same time, my Coke is absorbing a certain power of radiation. This time, the energy it loses per second by emitting this radiation is smaller than the energy that it gains every second by absorbing this radiation from its surroundings. So its temperature goes up. If you have something that is staying a constant temperature, it is because the power of radiation it's emitting is equal to the power of radiation that it's absorbing. So it turns out temperature and changes of temperature are all to do with the balance between how much radiation you are emitting per second and how much radiation you are absorbing per second. Careful, the misconceptions here are that the coffee does not absorb any radiation and the Coke does not emit any radiation. All of my objects both emit and absorb radiation, so we can have a little think about how this would affect the temperature of the Earth. But just so that I don't tread on geography's toes, I am just going to talk about this purely in terms of radiation emitted and absorbed. So for the temperature of the Earth to be increasing, it must be absorbing more radiation per second than it is emitting per second. And you can look at this with the lens of climate change, or you can just look at this to explain why the Earth cools down at night. So during the day, obviously the sun is there and lots of the radiation from the sun is being absorbed by the Earth. Some of that radiation will just be reflected, and also the Earth will be emitting some radiation too. At night, when the Earth is facing away from the sun, you have a larger amount of radiation being emitted by the Earth, which causes that decrease in temperature. When we're talking about global warming, the power of radiation being absorbed by the Earth is not equal to the power of radiation being emitted by the Earth. Then you will get the Earth gradually changing in temperature, which can cause the Earth loads of problems and scientists loads of headaches. If you like the video, please do give us a like and subscribe. Make sure you download the notes. Thanks for watching.